Hi, my name's Scott Williams. I'm with the Building and Safety Standards Branch with the province of British Columbia and main technical lead with regards to the BC Energy Step Code as well as the newly minted Zero Carbon Step Code. Sorry I couldn't be there in person. Thanks for having me. I'm hoping that this virtual pre-recorded version works for everyone. I will be calling in later for the Q&A session. So if you do have any questions, I will be able to answer them at that time. Basically, what I wanted to cover today is just provide a general overview of the key changes to the BC Building Code with regards to energy efficiency and carbon pollution. Also wanted to go over a study that was undertaken last year with regards to log homes to see where log homes actually line up in terms of the BC Energy Step Code requirements. So I'll go over some of the key highlights from that study as well. So, Clean BC outlined commitments to net zero energy ready for new buildings by 2032 with incremental steps to achieve this goal. So, we're now seeing the first mandatory step in the step code at step 3, which is 20% improvement in overall energy efficiency via performance based criteria and whole building analysis. So, with this graphic here, it just basically shows those incremental steps to that end goal of net zero energy ready by 2032. And here we are at May 1st when the changes did come into effect. And so we're essentially looking at step 3 for part 9 residential buildings and step 2 for part 3 buildings. So there are some caveats with regards to part 9 in terms of some of the exclusions with regards to log homes, and I'll be getting into that a little bit later on in the presentation. The step code has been voluntary for quite some time now. Since 2017, it got written into regulation, and local governments were able to opt into it as they so choose. But this now, with this new minimum mandatory requirement of that 20% improvement and the performance path, it is a significant shift in terms of the BC Building Code. Now, this performance-based approach and criteria are now the base code minimum. So what does that mean? So we have energy modeling that needs to be undertaken for most buildings pertaining to new construction. Air tightness testing is required as well too. And there's no prescriptive requirements to a degree, and there are some caveats to that, and I'll get into that a little bit later on. So it's essentially providing that latitude and leniency for any builder or designer to decide what works best in terms of their given project to reach those end outcomes in terms of overall energy efficiency. So it does provide a little bit of latitude and leniency, but at the same time does provide that criteria of how the building is supposed to perform overall in terms of energy efficiency. So like I said, step 3 is required for all part 9 residential, with the exception of log homes, and I'll get into that in a little bit more detail in terms of what that actually means. In addition to step 3 in the performance path, we also did develop a 20% better prescriptive approach. This was to address concerns raised by some local governments with regards to access to EAs and so energy advisors and energy modelers, as well as air tightness testing. So what we did is we essentially took the pre-existing prescriptive requirements in the BC Building Code and just essentially ramped those up in terms of RSI and U values to make them a little bit more stringent. So one key thing about this is this essentially needs to be unlocked by a local authority and needs to be adopted and written into bylaw for that in order for it to come into effect. So where a local authority chooses to allow for compliance with the prescriptive requirements, they may not restrict builders from voluntarily complying with the performance requirements of step 3, 4, or 5. And those can be considered an acceptable alternative to the prescriptive requirements. One other thing as well to note is that the language within 936 is a little bit different than maybe what you're used to, and that's just as a result of our harmonization commitments with the National Building Code. So we really wanted to marry the language that is currently within NBC 2020, and so you'll see that there is some changes in terms of the formatting of where that language is located. So what does this mean in terms of these new code requirements in the context of log homes? Essentially for log homes, it's status quo. So the prescriptive approach that you were used to in terms of what was represented in 936.2 to 936.4, including that trade-off path, those are still available to you. So that does not include the new prescriptive requirements to marry that 20% better improvement in energy efficiency. This is the pre-existing prescriptive requirements. And then also too, you still do have the performance paths available to you in terms of 936.5, or if you so choose, you can always still go the step code route via 936.6. So those options are all still available to you. So that new minimum mandatory requirement of step 3, not necessary for log homes. You just basically will follow what you're used to in terms of the status quo and those previous requirements. So there's one thing that we have included in the BC Building Code is a definition with regards to log homes. And so log homes shall mean homes with a type of construction whereby the exterior vertical opaque walls primarily consist of structural log members. So a little bit of clarity provided there. So now that I've gone over the code changes with regards to energy efficiency, now I just wanted to highlight some of the changes, key changes with regards to carbon pollution and the zero carbon step code. So in 2021, the province released its Clean BC roadmap to 2030 and included a commitment that all new buildings in the province must produce zero greenhouse gas pollution from their operations by 2030. So similar to the step code and energy efficiency, the province also established interim dates for mandatory carbon limits. So what these look like is essentially so very similar to the BC Energy Step Code. We have those interim milestones. So we have commitment for mandatory requirements in 2024, 2027, and the ultimate goal of zero carbon new construction by 2030. So in terms of the requirements of what we'll see in 2024 and 2027, that remains to be seen. It's still under development, but just know that those milestone commitments will be honored, and we will be following the same sort of route that we've taken with the BC Energy Step Code in terms of voluntary adoption and then it being ramped up over time with the milestones that have been outlined here. So very similar to the energy step code, the zero carbon step code is based on varying and measurable performance levels or tiers. So there are two new sections to the BC Building Code, Section 937 and Section 10.3, that local governments may use if they wish to regulate the greenhouse gas pollution produced by new buildings. So there's a couple of important key points that I want to clarify here. First, the zero carbon step code is not a part of the existing BC Energy Step Code. While the BC Energy Step Code addresses the energy efficiency performance of new buildings, the new Zero Carbon Step Code targets their operational carbon performance. So they are two separate and distinct regulations. Second, the standard only addresses the emissions produced by buildings during their operation. It does not regulate a building's embodied emissions at this time. So builders and developers working in communities that have adopted it will be required to demonstrate compliance with one of its levels. So regarding the different levels that you're seeing here on the slide, so we have both for part 9 and for part 3, we have a measure only as being that first initial step. So that's really very similar to the BC Energy Step Code in terms of step 1. And from there, we ramp things up in terms of increased levels of stringency. So the moderate carbon performance, or as you will see in the code, EL2, so emission level 2, typically equates to decarbonization of either the space conditioning or the domestic hot water systems. Achieving strong carbon performance, otherwise known as EL3 in the code language, would typically equate to decarbonization of both space conditioning and domestic hot water. And achieving the zero carbon performance, or EL4, would typically equate to decarbonization of all end uses. So with regards to occupancies that are regulated in the zero carbon step code, it's the exact same as what's regulated under the BC Energy Step Code. So for Part 9, similar to the Energy Step Code, this applies to residential construction only and does not include mixed use occupancies, nor does it include Part 9 commercial occupancies. Um, and with regards to Part 3, the zero carbon step code, similar to the energy step code, applies to Group C, D, and E occupancies. So that is Group C is residential, Group D is business and personal service, and Group E is mercantile. So a lot of similarities in terms of what you currently see within the BC Energy Step Code in terms of those occupancies. So what does this mean in terms of compliance options with regards to Part 9? So there's three compliance options for Part 9 residential buildings. So we have absolute metrics that you see on the left-hand side of the slide. And this is basically the total kilograms of CO2 equivalent per year. And we also have intensity metrics. So you see here on the right-hand side, and this is with regards to total kilograms of CO2 equivalent per meter squared per year. So it's based on the floor area of the building. And then we also have prescriptive requirements as well too. So I'll get into that a little bit in more detail in the next slide. So one thing to note is that both the absolute and intensity options require using software to calculate how much operational carbon pollution the home will produce. Um, you also might be wondering why these values in terms of the most stringent do not actually show a value of 0. This is really as a result of emissions factors associated with the electricity grid. And even when you're trying to use the cleanest fuel possible, you're not necessarily going to get there in terms of total elimination of carbon emissions from the operations of your building. So as the greening of the grid continues to develop, we will be getting to 0 at some point, but just we aren't at that point just yet. So what's included when you're demonstrating compliance with the zero carbon step code in the context of Part 9? So with regards to the performance pathway and looking at total GHG or GHGI in terms of the greenhouse gas intensity, we're really looking at the main systems of the building. So we have space conditioning and domestic hot water and ventilation. And it also includes supplementary equipment as well too. So this refers to equipment that is used to supplement the principal heating system when the capacity of the principal equipment has been exceeded. So a couple examples of this can include an air source heat pump with supplementary gas furnace, or an air to water heat pump with supplementary gas boiler, or a packaged dual fuel system such as an electric heat pump with supplementary gas heater. So one thing to note is that when you're following a performance path, it does not actually include all end uses. And so things like gas cooktops or gas dryers are not necessarily included within the calculation methodology. One thing to note as well too is that for both the performance and the prescriptive pathway, there is that exclusion with regards to backup or redundant heat. And so this basically refers to equipment that's installed in addition to the principal heating system, is independent of the principal heating system, and is not designed to meet the space conditioning load of the house. So an example of this can include wood burning stove, also gas fireplace or emergency backup equipment. So that is excluded from the calculation methodology. And like I said, this applies both to the performance and the prescriptive pathways. In terms of the prescriptive pathway, it actually is a little bit more stringent than the performance pathway in that it includes all building systems and equipment and appliances. So it does bring into the fold things like gas cooktops and gas dryers. There still is that exclusion with regards to backup or redundant heat. So things like gas fireplaces would not be included in the calculation methodology. But what we are doing is we are working on the methodology to include all of those end uses so that when we say zero carbon performance, we actually truly mean zero carbon performance. So that's still under development. And so we hope to have something out fairly soon in terms of providing further direction with regards to that. So here's an excerpt from the BC Building Code in terms of the requirements for GHG emissions for Part 9 buildings. Before I get into this, I just wanted to reiterate the fact that there are two emissions factors that are currently within the BC Building Code, which apply across the entire province. And these are for electricity and natural gas. Um, Fully understanding that there are regional differences across the province in terms of different grids and different associated emissions factors. However, we wanted to take a consistent approach to define the GHG requirements. This was basically the easiest way of us doing that. And so one other thing to note as well too is that a bulletin was released on May 1st, which included additional emissions factors, such as emissions factors associated with things like propane or wood. And so the AHJ or authority having jurisdiction can use those at their discretion. And what we will do is we will take those and fold them into the next version of the BC Building Code. So we do have a more comprehensive list within the code itself. One thing to note as well too is that RNG, renewable natural gas, is not a compliance option for the zero carbon step code, because really there's no way at the time of design and construction to determine if buildings will be using renewable natural gas or not. It could be potentially used at the discretion of the authority having jurisdiction, but just know that within the BC Building Code itself, it is not considered a compliance option. So with regards to this table, a little bit complicated, so I'll try and get through this and provide a little bit of clarity. So on the left hand side here, you basically have your different emissions levels. So EL1 is the least stringent, EL4 being the most stringent. EL1 is essentially that measure only, so very similar to step 1 of the BC Energy Step Code. It's just basically analyzing the building and providing that value in terms of what that GHG output is, without any requirements as to meeting any sort of certain metrics. What we really tried to do with these requirements was we really wanted to focus on intensity metrics in terms of having a GHG requirement per meter squared of floor area. But we quickly realized that with Part 9 and all the different archetypes, it was really actually quite difficult for small buildings to meet the requirements, and quite easy for large buildings to meet the requirements, despite the fact that they both have very different emissions profiles, and larger buildings obviously emit quite a bit more in terms of greenhouse gas. So what we ended up doing is that we broke this out in terms of looking at absolute GHGs, and these are for smaller buildings. And then we looked at this middle column right here. This really applies more to medium-sized homes or large homes. And then this furthest right column is associated with the prescriptive requirements. So what we essentially did was this, is that if you, for any different project that you're working on, if you, as a log home builder, say you are following the performance path in terms of doing the energy modeling for your building, you will, as a result of that, be able to calculate your greenhouse gas emissions as well too. If that's the case, then following the performance path, you'd essentially be starting from left to right. So you look at the leftmost column, see where you land in terms of meeting these absolute metrics. If you don't meet them, then you would go to these middle columns, and you would need to meet the requirements of both of these columns for any given emissions level that you're trying to achieve. So we have the GHGIs, so the intensity metrics, and then we have the absolute values. So essentially, the intensity metrics are really meant for medium-sized homes, and then these absolute values is essentially an upper cap for those larger type homes. So meeting both the values within both of these columns, For a medium-sized home, not a problem really meeting this. This is going to be really the more stringent of the two, and no issues at all with meeting this because their GHG output is inherently less than a larger building. Conversely, a larger building, this is what would really dictate what whether or not they're going to comply or not, and they would have no problem complying with the intensity metric because they have such a large floor area in the denominator. With regards to the prescriptive path, this really marries in with sort of the general approach with regards to the different emission levels. So for EL2, we're really looking at decarbonization of the heating system. For EL4 or EL3, sorry, we're looking at decarbonization of both the heating system and the domestic hot water system. And then for EL4, we're looking at all equipment and appliances. So basically, for the prescriptive path, this can be followed by anyone. They do have that option. A local government cannot restrict you from using this. So in the context of log homes, if you're not following the performance path with regards to energy efficiency, you're not going to be calculating your GHGs. If you do find yourself within a jurisdiction where a local government has chosen one of these levels, then you would basically be going straight to this prescriptive path column. And so that would dictate what you would need to do in terms of your heating systems, your domestic hot water systems, and then all of your systems and all of your end uses. So because you're maybe not following the performance path doesn't preclude you from not having to comply with the different emission levels that are maybe being requested by a local government. So look at those prescriptive values, and that's what's more than likely going to dictate in terms of a log home. So as I stated earlier, embodied carbon is not something that is currently included. We're really looking at the operational greenhouse gas emissions associated with the building use. But just know that there is development that is happening with regards to embodied carbon. We fully understand that with regards to log homes, the embodied carbon piece is really one of its main attributes. And the reason why we haven't necessarily gotten to the point of including embodied carbon at this point within the BC Building Code is just due to the inherent complexities of doing so. So working at a calculation methodology, using something that is potentially an industry standard, and also to working with our national counterparts as well. Nationally, this is something that is being developed. You'll see on the screen here in the slide that nationally, they're looking at that operational carbon piece and those requirements in terms of the next code cycle for 2025. And then they're looking at embodied carbon. They're proposing that that's going to be in regulation by 2030. So, as you know, within BC, we've really kind of jumped the gun in terms of that, the timelines that are outlined for the national code process. Who knows what's going to happen as we move forward with embodied carbon? We may take the same approach. It just remains to be seen what actually comes of the development through the national code process. So that national process will definitely help to inform the provincial code as we move forward with it. So on to the log home study. A study was conducted, like I said, last year to really get a much better idea as to how log homes actually perform in the context of the BC Energy Step Code. So we really wanted to figure out how the metrics really lined up with the actual performance of log homes. Um, Consultants were retained, so Focal Engineering and Bernhard Contracting took a look at this. And what we essentially did is we engaged an advisory group to help guide this process. So a number of members of the Log and Timber Association were sitting on that advisory group. And what we did is we lumped this in. So we didn't look at log homes exclusively. We also looked at small homes in cold climates and looked at the analysis across the entire province. So In the context of log homes, we chose three different archetypes, and these were vetted through the advisory group to see what was kind of really the most sort of common archetypes that were being built within BC, so we could really sort of draw some sort of pragmatic conclusions based on that analysis. So really, the whole premise behind the study was the underlying notion that log homes can struggle to meet step code requirements due to the limitations of log walls and the R values associated with those log walls, as well as the perceived issues with regards to potential issues with air tightness testing as well too. So very similar to what I was just saying with regards to embodied carbon and the ongoing work with regards to that, it is well understood that log homes provide benefits beyond just energy efficiency, such as their use of regional low carbon materials, which are not currently regulated within the BC Building Code. So we fully understand the benefits of log homes, and the regional impacts that it has, as well as carbon sequestration and low embodied carbon. We're not there yet. We're looking at energy and operational carbon at this point, but we will get there eventually. So here are the three different archetypes that were selected for the analysis. So we really tried to have some degree of variation, but at the same time represent more commonly built archetypes within BC. So a couple things that I'll go through with you is that, you know, like in terms of the floor area, we have some variation, but they're actually not really all that big in terms of homes. Um, what we found in general with regards to energy efficiency and all the analysis that we've done in terms of the development of the step code is that smaller homes, in terms of energy efficiency, it tends to be a little bit more stringent in terms of meeting step code requirements. So that's in line with, you know, kind of the general thinking. Smaller homes, it's a little bit more challenging to meet step code metrics. So we've kind of focused our attention more on the smaller archetypes, knowing full well that larger homes are just going to be that much easier in terms of meeting the requirements. So we have a number of different stories. So we have a single story here. We have a single story plus a loft, and then we have a two-story. You will note, though, that the floor area for the two-story, this is actually the smallest of the three. We have varying below grade conditions. So we have conditioned crawl space as well as basement conditions. And then also too, we have varying degrees of window to wall ratio. So that's basically just the percentage of glazing in relation to the opaque wall assemblies. And then as well too is we have this VFAR. So essentially what VFAR is the volume to floor area ratio. This really indicates some of the kind of the compactness of the building. So the more articulated the building is, so the more ins and outs, the more jogs, the more dormers it has, the worse it's going to be in terms of that VFAR value, the higher that value is going to be. So that essentially that form factor plays a very significant role in terms of how a building will eventually perform with regards to energy efficiency. So as you see here, we have really this single story plus loft is the most compact in terms of that metric, whereas this smaller home, this two-story home, is actually the highest in terms of that metric. So this is the least compact of the three. You will note as well too is that we have uh, some framed walls as well too. So the second story, so that loft space for this archetype does have some framed components at the top. And then for the second level of this one, this is all framed as well too. And so really predominantly we have really the log structure being that primary, that single, sorry, that the first story of the actual building itself. Um, in terms of the rationale behind why these were selected for this one, it was really because it's more highly articulated in terms of that T shape. So we wanted to see how that actually worked. We have the typical tugboat style, so we actually have quite a bit of glazing on one of the elevations, as you can see. And then for this last one, this is kind of like a more standard type of configuration. We have dormers up top, and we actually have a vaulted ceiling at the front of the building here as well too. So that indicates that there's more volume inside the house and less floor area, which is somewhat detrimental in terms of actual energy performance. So just at a high level, this building right here, the one with the loft, it generally performed best of the three log home archetypes. Really, it's due to its compact form in terms of that VFAR value. And the worst performer out of the three was the two-story home, which is the smallest building. So that's like I was saying, in terms of smaller buildings, this is somewhat in line with what we were expecting. So medium and larger homes generally face less challenges than smaller homes in achieving step code metrics. This is due to the to less floor area in the denominator for the intensity metric. So as you know, for the step code, we do have intensity metrics, which are basically the energy used based on floor area. So if you have a smaller home, you have less floor area in that denominator, and then so that makes it a little bit more challenging in terms of meeting those requirements. Also, too, for smaller homes, is that base loads are disproportionately higher, such as domestic hot water. So you're going to have domestic hot water systems, obviously, in all three of these buildings, which is largely going to be the same for all of them. And so it actually has more of it takes more of the energy pie, so to speak, for that smaller home, as opposed to a larger home. And also too, for the percent better than metrics that we have within the step code as well too. Small homes are typically more efficient to begin with, so to make any changes to that building in terms of providing more of a percent greater improvement, it's actually a little bit more challenging because it's inherently a little bit more energy efficient to begin with. So in terms of how the analysis was actually conducted, there was a number of energy conservation measures that were implemented. So these ECM values, and these are basically different levels of stringency in terms of the different systems within the building. And we did a bunch of iterations with regards to energy modeling to see what the potential outcomes were. So on the left-hand side, you'll see what's listed in terms of those different components and systems of the actual building itself. In terms of the base scenario, this is essentially base code compliance. And now it's informed what the base case was. And like I said here, these are all the different values in terms of what the different iterations were in terms of what we did in terms of the analysis. So I'll just go through a couple of the key ones. In terms of air tightness, the air tightness value that we used for the base case was whatever it was for that given step. So for step 3, we had 2.5. For step 4, we had the ACH value associated with step 4, and so on and so forth. What we did do in terms of varying it is that we took that step 3 value at 2.5 as being one of those values, but then we ramped it up in terms of 1.5 ACH and 1.0 ACH just to see what the potential outcomes were with that. With regards to the window U values, here are basically the base building values, and this refers to climate zone 7B and up, had a U value of 1.4. What we did is we varied those from 1.4 all the way down to 0.8. 0.8 being a very well performing window, so that essentially is equivalent to passive house standards. Solar heat gain coefficient, we had 0.3 in the base case, and then we just actually increased that slightly just to see what would happen in terms of improved solar heat gain during the winter months to try and take advantage of those heat gains in order to reduce the energy demands. In terms of the log walls, what we did is this: is we had an R5 value for machine log walls, and then we had an R value of 10 for hand milled logs. So what we did in terms of that ECM, that energy conservation measure, ramping up that stringency, is that we ramped it up to R15. So the machine milled, we included an actual liner on the inside of it, so an additional stud framed wall on the inside of that to get it to that effective R15 value. And then we, for the milled, we also had just a larger diameter with different species, and we got that to the R15. One thing I will note is that we did not actually price this R15 because we weren't actually able to get some accurate data in terms of what the cost was for that increased diameter and different species. So that is something that wasn't actually priced within the actual analysis itself. In terms of framed walls, like you saw with the archetypes, there's some areas where we actually do have framed walls, typically on the second story. So we have the typical R values based on climate zone for the base case, and then we just basically ramp those up slightly to have increased thermal performance. Same thing with the ceiling, started with our base case here, and then ramped it up to R40 and R50. We did have no insulation under slab for those below grade spaces in the base case, and then ramped it up to R5 and R10. And then also for the below grade walls, we had R12 for the base case, and then increased it to R17 and R22. In terms of the systems that were used in the building, fairly basic. We didn't tinker with these too much. So for the domestic hot water system, started with an electric tank, and then we went to a heat pump tank. A heat pump system. And then for the space heating system, electric baseboard is what we had for the base case, and then we ramped that up to a heat pump system, so an air source heat pump, and it had an electric backup. Maybe not necessarily purely representative, especially for log homes that are going into colder climates. Nonetheless, it does provide us with a little bit of comparison. So basically, through all of these ECMs, there's a bunch of combinations and permutations in terms of all the changes associated with these different values, which meant thousands of modeling runs to see what the potential outcomes were. So here is an example of what some of these outcomes actually were. So essentially, what we're looking at is that single story. So it's like the medium performer. It's not the loft archetype that was the best performer, nor was it the smallest archetype that was the worst performer. So this is kind of right smack dab in the middle. So what this chart is essentially showing is that on the left-hand column, we have the different R values of the actual log wall system. So we have an R5, an R10, and an R15. So this represents that larger diameter and that different species of log. What we looked at is for all the different steps, so 3, 4, and 5, for each of the different R values, what combinations of those energy conservation measures, how many of them are going to lead to positive outcomes in terms of meeting the step code requirements? So you'll see here that with regards to if you're starting with an R5 wall and you're varying all those different energy conservation measures in terms of like air tightness and window performance and all those other metrics, you'll see that, there's 111 combinations of ECMs that could potentially be used in climate zone 4 and climate zone 4 only to meet step 3. But as soon as you get beyond step 3 and beyond climate zone 4, all of a sudden there's really no values that would meet those requirements. So that indicates that that R5 wall is really not necessarily the best way to go in terms of looking at overall log home performance. One positive note to see here is that R10, in terms of that R value for your log wall, for all of the different steps, we're seeing that for step 3, across all climate zones, we actually have quite a few different options in terms of meeting step 3 with various combinations of energy conservation measures. So that's a really positive sign that indicates that with this sort of middle of the road home, we're able to meet step 3, and we have quite a few options in order to do so. With regards to step 4, we're seeing that this is somewhat diminished. However, there are still some options here. But as soon as we start to get to the coldest climate zones, we no longer have any options. For step 5, we have a few options for climate zone 4 and then none for the rest. When we look at the R15 wall, it would make sense that because of the improved thermal performance, the actual log wall system, we're going to have even more options, in which we do. And sorry, my ugly mug's in the way at the end there. I don't know how to actually move that. So at any rate, take my word for it. The R15 wall is obviously the better performing, and then so you have more options to choose from there. So here is an outline of what this actually means in terms of cost. So this is a chart of the incremental capital cost in terms of percentage. And we're looking at the R10 wall system. We're looking at that same archetype, so that single story, so that middle of the road archetype. And what we've done is we've essentially taken a medium home that we have from the metrics research report, that is a standard stick-built type home, conventional home, and to see where these all actually line up. So basically what we have is that this gray bar indicates the range of ICC percentage, so the incremental capital cost in terms of percentage. And what we have in terms of the actual average of that range is represented by the orange dot. And then the blue dot represents that average associated with a conventional stick-built home, a medium-sized home, which is somewhat similar to the size of the home that we analyzed in terms of the log home archetype. So what you'll see here is that the range in terms of ICC varies quite a bit when you go from the different steps. So this is step 3, 4, and 5 for all the different climate zones. So this is step 3, 4, and 5 for climate zone 4, step 3, 4, and 5 for climate zone 5, so on and so forth. So what you'll see is that with the log home, it really follows the same trends as what you see with the blue dots. So very similar in terms of the outcomes for a conventional home. They're just a little bit higher. One thing I will note with this, though, is that there's a couple critical things when looking at this, is that this single story log home is not necessarily the most compact in terms of its building form. It has that T shape, so it does have some articulation, so it's not necessarily just a box. And that remains static through the analysis, so there's not any variation with that. Another thing that's static as well too is that window to wall ratio that we looked at when I was outlining all the different parameters for all those different archetypes. That remains static as well too. Another thing that remains static as well when we're doing this analysis is the building orientation. So where the glazing is associated, the most glazing associated with the different elevations to take advantage of potential solar heat gain during the colder months of the year. So because all those things are static, those are all things that can, for any individual project, can be varied as you so choose. Obviously, given site constraints, but these are things that don't necessarily cost anything, right? You can vary your window to wall ratio to be more optimized in terms of increased energy performance. You can vary the form slightly to have a more compact form in order to take advantage of energy efficiency as well too. Again, the orientation of the building as well too. Given potential, given site constraints, you might be able to actually take advantage of that as well too. So these are all just considered zero cost measures, which have a profound impact on the actual outcomes of the building. So even though you're seeing here that there is that incremental capital cost that is a little bit higher than what you would typically see with a conventional home, doesn't necessarily mean that it's way more expensive for log homes going through this process in terms of energy analysis. So that's just one thing that I wanted to point out. And understanding full well that with regards to log homes and the R value, the effective R value of your opaque wall systems is a fairly serious detraction in terms of the overall performance of the home. And you don't necessarily have that with a conventional home. And so you're inherently behind the eight ball with regards to logs thermal performance. And you will need to make that up by other means. So yes, there will be some variation in terms of that incremental capital cost. I just wanted to put it into context with regards to, understanding that there are a lot of things that weren't necessarily absorbed in this analysis that can be used as design measures to really, like I said, profoundly affect the overall energy efficiency of the building. So, this is a pretty interesting chart as well too. This really indicates, again, we're looking at your single story log home, same archetype that we've been looking at for this analysis all along. We're looking at climate zone 6 and for step 3 and for an R10 wall. And so what this is actually showing us is that we have all of our different systems or components on the left hand side. And what we have here is this basically shows what systems or changes, so the ECMs that I was talking about earlier, what that will do in terms of your overall percentage improvement. And so when we're looking at meeting step 3 in climate zone 6 with an R10 wall, if you have an electric domestic hot water tank, 60% of the time you're going to be meeting those step 3 metrics, right? In terms of heating, if you have an air source heat pump, you're more than likely going to be meeting that a little bit less than 50% of the time, but electric baseboard heat, you're actually meeting it for over 50%. So in terms of that cheaper sort of like more redundant sort of system, the electric baseboard heat is something that could potentially be used and not necessarily be a detriment in terms of the overall energy efficiency. The efficiency of electric baseboard is 100%. Air source heat pump is going to be higher than that in terms of the overall efficiency, but in the grand scheme of things, you're actually doing okay if you're using baseboard heat. With regards to, say, a heat recovery ventilator, if you don't use an HRV, you still have a 35% chance of actually hitting step 3. This is, I mind you to take this into context of all the different energy conservation measures as well too. This is a very somewhat simplistic way of looking at it, but it actually is really quite telling. And then in terms of the heat recovery ventilator, in terms of the efficiency of 65%, you're gonna have anywhere in between. It's looking like around close to 35% in terms of your effectiveness of actually meeting step 3. One thing I found really interesting here is windows, and again, I'm sorry, but the caption is down on the bottom right. With regards to a U value of 1.6, if you're using a U value of 1.6 in the analysis that we conducted, the percentage of you actually meeting step 3 is approximately 5%. So you're really wanting to look more towards those higher performing window types in order to increase your chances of actually meeting step 3. So pretty interesting. Like I said, a little bit simplistic, but at the same time, I think it actually conveys quite a bit of information. So what are some typical solutions that can really be looked at to improve energy efficiency and airtightness for log homes. So these are like I said earlier, these are kind of they're perceived to be the two biggest things in terms of like your log walls and the R value of your log walls and being an inherent detriment in terms of your overall energy efficiency. Also, as well too, is you have all of those joints associated with your log wall systems, and so there's those issues with air tightness as well too. So what are some typical solutions that you can look at to help further you down the road in terms of meeting more stringent energy efficiency requirements, as well as meeting higher air tightness testing values as well too. So like I was saying before, is that your building form is really a critical player in terms of the overall energy efficiency of the building. So the graphic on the right gives an overview of what this actually means. So Teddy, this is just referring to the thermal energy demand intensity. So it's just kind of the performance of the building envelope. And it just means that a higher Teddy value means that you need more energy to maintain it at a certain temperature of 21 degrees Celsius in terms of that internal temperature. So working from left to right, you have a very simplistic form. With lower Teddy, you articulate that building a little bit more. So you have an L shape, you got a couple dormers, you got a little, I don't know what that would be underneath here, but maybe that's a garage. It increases that envelope surface area, and then so you're actually going to have more energy required in terms of that input to maintain that same temperature that you would for this one right here. Keep on going. If you got a bunch of bump outs as well too, then that value is going to change as well. So you can see that with compact form, it makes a considerable difference in terms of what that actually means in terms of the overall energy performance. So these are things that are at your disposal when you're thinking about the design of a log home. Doesn't necessarily mean that you need to go to the nth degree and create a log box. That's not what I'm insinuating here. But like looking at the different archetypes that we looked at with the study, there was some articulation there, and they're still able to meet those step 3 requirements, right? So um, that's one thing that you can use in your toolbox. Another thing is too is really optimizing your glazing and that building orientation. So like I was saying before, you really want to be taking advantage of the solar gain that can be gleaned during the winter months. So you want to have that solar radiation that's getting in deep inside the building, based on the angle of the sun in the sky to reduce your requirements for energy, essentially, right? So again, you have that at your disposal. Obviously, there's going to be potential site constraints, but at the same time, this is still something, it's a somewhat simplistic measure that can be considered and can have a very profound effect. So the location of glazing, where are you locating it? Is it more on the south side? Is it on the east and west? Are you taking advantage of that solar heat gain? One very important thing about this is if you're taking advantage of that solar heat gain, you really need to be cognizant of overheating. So with log homes, the beauty thing about log homes is they typically have sizable overhangs, which is actually really quite wonderful. So when you have a very high angle of the sun in the summer months, then the shading is going to be great because you're not going to have that unwanted solar heat gain during the summer months and causing some occupant discomfort as a result. However, based on the design of those overhangs in the winter months, that sun's obviously lower in the sky, you can get that sun penetrating deep into the space. Another thing that you can think about as well too is the window to wall ratio. So if you have less window, more wall, it's inherently more thermally efficient, and so you can make these design choices. Again, this is not necessarily going to cost you anything in terms of doing so, but does have an effect on the overall energy efficiency of the building. So, in terms of the actual thermal performance of the building itself, like we saw in the archetypes, there were below grade spaces and there are also framed walls that were being used on the second levels. take advantage of those as much as you possibly can. You're not restricted to a certain R value as a result of these different systems as you are with your log walls. So there is the potential to bolster the thermal performance of the building based on your below grade systems, your roof systems, and your framed wall systems as well too. So try and take advantage of those as much as you possibly can. With regards to air tightness testing and improved air tightness performance, um, really it's all those interface details, right? As you know, like basically window penetrations are huge. You got a big hole in your wall system. So what do you need to do in order to maintain that continuity with the air barrier? Um, Obviously, with log homes, there's those considerations with regards to shrinkage and movement. So that needs to be incorporated in terms of that potential deflection with that window system. So in terms of caulking, flexible membranes, what can you potentially do to maintain that air barrier continuity with your window systems? Um, so anecdotally speaking with builders that have worked on a number of log homes, undergone the energy modeling process as well as the air tightness testing, what they've found is that it's not necessarily the opaque wall systems themselves. So the log walls that are really causing the issues in terms of that air leakage, it's really more those interface details. So those it's like corners, or where those log walls interface with dissimilar components, such as your log wall to foundation wall interface. What are you doing there to maintain your air barrier and make sure that there's that air barrier continuity? Um, Also, too, a lot of missed opportunities are at the log wall to roof interface as well, too. A lot of times that gets missed during construction. It's not pre-stripped properly or not pre-stripped at all. And so that means that you essentially have those potential air leakage points as well. So little information on a building that was built in Nanaimo. And there's some issues during the air tightness that I just wanted to highlight. And so one of them being is that, like I said, at the log wall to roof interface, it wasn't properly pre-stripped here, and there's some air leakage associated with that lack of continuity at that interface detail. Also, too, we have this beam to outside wall interface, and there's some air leakage there associated with lack of continuity. And then if you look here, this is a thermal scan during an air tightness test. So basically, purple's bad. That means that it's cooler, and red is good. That basically means that it's not losing any energy. So what we're seeing here, and this is the actual live shot of that same thermal image, is that you can see that there seems to be some sort of discontinuity at that window to wall interface. And so something that needs to be considered when you're detailing your windows, obviously. In terms of like wrapping membrane inside the rough opening and doing a very sort of conventional type membrane detail, so you have continuity of your water resistive barrier as well as your air barrier, and transitioning to that to the back of the window. Something that should be definitely considered in terms of maintaining that continuity to the back of the actual window system itself. And here is the foundation wall to floor interface. So here's the shot, and here's the thermal scan. So it looks like they forgot both the insulation and the air barrier, because we're seeing a whole lot of purple there. So again, where you have those transition details between dissimilar components, take a look at those, make sure that you have continuity. And these are all things that obviously like can be addressed during that initial sort of like framing or installation of those log walls during those initial stages, to make sure that all I need to do is pre-strip this properly, then I can plop everything on top of it, and then we're all good to go, right? So it's just a matter of having a little bit of forethought with regards to the sequencing as you're going through that going through the construction process. So thanks very much. I hope that was really useful. A lot of changes with regards to the BC building code, with regards to log homes. Obviously, with regards to energy efficiency, status quo is where you guys are at. We'll see what transpires with regards to future iterations of the code and the analysis that was done with regards to log homes to see how these actually line up and what future changes we could potentially consider. So thanks very much. Thanks for having me, and I hope this was helpful.